All right, here we go. The last part of this chapter. Trig section 1.5. We are proving trig identities. Right, here's a list. This is going to feel a lot like the section on simplifying trig expressions, only now you have another side of the equation. And what that's nice for is that you know if you got the problem right, because at the end of the problem, the two sides should look the same. And if they don't, then you got to keep going. So here is the list that I started in that section on ideas of what you can do. This is not a 1, 2, 3 ordered list. This is a list of things to try or things that might help. So one is changing everything to sine and cosine. That's one we talked about before. Sometimes that's helpful. You can add fractions. Okay, you can use the Pythagorean identities. To substitute stuff out. You can multiply things out. If something's squared or multiplied by something else, you can multiply that out. Sometimes that's helpful. You can factor. You can multiply by the conjugate. That might be a new word. We'll talk about that. And you can split up fractions. Okay, those are some ideas, and what I'm going to do is try to do a couple of examples that hit on each one of these. So the first example we're going to do is tangent of x over secant x equals sine x. Okay, now there's only one rule with these guys. You cannot move anything across the equal sign. I don't think that's how you spell across. That looks better. All right. So, it's not like solving an equation where you could add 3 to both sides or something like that. You kind of have to treat it like two separate problems. I like to envision a big, long brick wall right here. Okay. Nothing goes across this wall right here. So you get to pick a side and you get to work on that side. So for example, on this problem, you cannot clear out the fractions. You cannot multiply both sides by secant x. Okay, you just pick a side. Now typically, I pick the side that looks more complicated. That's how you choose where to start. But sometimes they both look complicated, and then it's kind of just a guess. You pick one and hope it works out, and if it's not working out, you can start over and try the other side. So, and in addition, I mean, if I picked this side with sine x, I mean, there's nothing really to do with that. It's not interacting with anything else, so it's hard to create something out of that. All right, so I look at this, and it looks like it's a pretty simple fraction. It's already added. I'm going to try to, change these to sine and cosine. So tangent is sine x over cosine x. That's my numerator, rewritten in terms of sine and cosine. And secant is 1 over cosine. So in this sense, it's very much like those simplification problems, because you're just kind of forgetting the right-hand side, and you're just simplifying. So you're doing a lot of the same stuff, which is why we did that first, to get you comfortable with that. And then you're just trying to get this to look like the right-hand side. Waiting for something magic to happen. So the cosines cancel, and oh, look at that. I'm just left with sine x. And when these guys match, then you're done. Okay, so this is an example of how to rewrite with sine and cosine. Okay, let's try another one. Let's do number 2 here. Okay. Again, no moving things across the equal sign. This is going to be an example of what happens when you multiply things out. So I look at this left-hand side. Everything's already in terms of sine and cosine, so that's not really an option. But this left-hand side has something to multiply, so maybe something magical happen if we do that. Let's write it out. That 2 does not distribute. Do not do it. Okay? This is a big foiling problem here. So you got sine squared x. You've got sine cosine. Then I've got sine cosine again. And cosine squared. Okay, so the middle 2 terms add up. And this should, right here, raise red flags. You've got a sine squared plus a cosine squared. If you have not memorized those Pythagorean identities yet, you need to do it now. If they're not in your brain, you won't recognize them when you're in the middle of this problem. So they need to be memorized so that they trigger something in your brain. These together combine to give you 1. Okay, and I'm still left with this middle term. And oh my gosh, there we are. I've just matched the right-hand side, and I'm done. Okay, so that's an example of multiplying out, and I guess a little bit of Pythagorean theorem too. All right, next problem. I'm going to do tangent squared minus cotangent squared equals secant minus cosecant. All right, now, which side do you want to start with? I have no idea. So I just choose one to go with. I'm going to work with the left-hand side. I see 2 things. My brain automatically sees that there's a bunch of squares, which to me is a Pythagorean identity dream. Okay, so that's an option. The other thing that I see is that these guys are both sides are a difference of 2 squares. Okay, now which road you choose to go down is up to you. The other thing I see is that I've got a lot of secants, cosecants, cotangents. I could write everything in terms of sine and cosine. So there's 3 potential roads right there that I can see that you could go down. And you just choose one. And if it gets hard and you don't know what to do next, then you stop and you try one of those other roads. Okay? The first thing that I'm going to do is I'm going to use the Pythagorean identities. So let's remember what those are. Sine squared, cosine squared equals 1. And then I have 1 plus cotangent squared equals cosecant squared. And I get that one by dividing through by sine. And then if I divide that first one by cosine, I get tangent squared plus 1 equals secant squared. So I just figured those out at the beginning of my test, write those at the top. And I want to substitute, so I'm looking here first at tangent squared. And the other thing that I got my eyeball on is the other side of the equation. So I want tangent, and over here I've got secant, right? Well, look at this Pythagorean identity. That turns tangent into secant. So that's a real good clue that this probably is going to work, okay? So if I want tangent to be substituted, then I'm going to subtract this 1 over to the other side. And I get secant squared minus 1. So this is what I'm going to substitute in over here. Secant squared x minus 1. Then I've got a minus sign. And now I'm looking at cotangent. All right, that's this Pythagorean identity. And I want to figure out what cotangent is, so I'm subtracting 1 across. And cotangent looks like it's going to be cosecant minus 1. So this is what I'm going to substitute in for cotangent squared. Okay. And then I'm going to distribute that minus sign in. See, at this point, I'm like, oh, I'm in business because now I've got my left side in terms of what's on the right side. So you know you're barking up the right tree. All right, distribute that minus sign in. This -1 and +1 are going to cancel. And I get secant squared x minus cosecant squared x. And yay, I'm done. Okay. Now, I think it's instructive to see how to do problems multiple ways. So I want to do this same problem a different way. Everybody's brain looks at things differently, and so different people have different ideas. One thing you could do with the left hand, I'm going to again just work with the left hand side. You could start on the right hand side. I could turn everything in terms of sine and cosine. So tangent is sine squared over cosine squared. And cotangent is cosine squared over sine squared. And now what I've created is two fractions, which I now can add together. So I'm going to get a common denominator. Okay, so I end up getting sine to the 4th minus cosine to the 4th on the top. And then I've got a sine squared and a cosine squared. Okay? This is the difference of two squares. Now, why do I do that? Because I'm looking here and saying, okay, the powers that I have going on in this problem, these are fourths up here. And over on this right-hand side, they're only squareds. Well, if I can factor things, that drops the powers, okay? And so that's my kind of clue that says, well, maybe that might be helpful. So it's the difference of two squares. We've seen that power pattern before. So this factors as a plus and a minus. Whoop. All right, over this fraction. And this should register as a Pythagorean theorem. That's equal to 1. Now, I'm going to show you maybe a new trick, maybe something you haven't seen before. When you have one term on the denominator, so notice that there's no addition subtraction here. What you can do is you can split that denominator up under each piece of the numerator. That is legal. It's like kind of like unadding the fractions, so to speak. And the reason that you might want to do that is if you notice the left-hand side here is all one fraction. But the right-hand side over here is two pieces connected by subtraction. So it's broken apart, whereas the left side's not broken apart. So whenever you're in that situation where one side's broken into two terms and one is an entire fraction, this is the trick. And this is what I mean in our list. This is the the split fractions trick that I have right here. That's what I mean. Take the denominator and split it up between the two, and look at what happens. Oh, wrong color. Sine squared x over the whole denominator minus cosine squared x over the whole denominator. And what that does is it eliminates that subtraction sign from the fraction, and now you're allowed to cancel because this is multiplication. Everything's multiplication now. And so I can cancel the sine squared x, I can cancel the cosine squared x. And this is left with 1 over cosine squared minus 1 over sine squared, which is secant squared minus cosecant squared, which is what our right-hand side was up here. Okay, so now I think that way is a little bit longer, but it's not bad and it's not wrong. It's just different. And if that's what you see first, then you just run with it. And if you get to a place where you don't know what to do next, then maybe go back and try something else. Okay, so that was an example of splitting the fraction and writing in terms of sine and cosine. This previous method up here was using the Pythagorean identities. Okay, let's do a couple more. Practice on these things. Practice makes perfect. Okay, the more you do, the better you will be. Okay. In this example, I want to introduce the idea of multiplying by a conjugate. So where you've seen conjugates before was in Algebra 2 when you did imaginary numbers. You did like 4 over 3 plus I, and the way you handled that situation was you multiplied by that denominator with an opposite sign, and this is called the conjugate. So the conjugate is when you have a two-term polynomial, you multiply by that same two-term with the opposite sign in between. Okay, when you do that, you're creating a difference of two fractions, and some nice things happen, especially in trig. And in order to keep it even, you can't just go multiplying the denominator by something. You have to do that on the top as well. And so we're going to do that same thing here. And the pattern that makes you draw towards the conjugate is this right here. When you have 1 and a trig function, either plus or minus, but nothing squared, the conjugate is often a best bet. Okay, so if I had, for example, a problem that had 1 plus cosine in it somewhere on the top or the bottom, you got to have a fraction, okay, over something. That would be an indicator that maybe I want to multiply by the conjugate. And this pattern, this 1 plus or minus a trig function, it can be on the top or the bottom. It doesn't matter. If I had 1 plus tangent x somewhere, then that would be a clue that maybe I'd have a conjugate. So those are the kind of things. So let me show you what happens when you do this. I'm going to multiply by 1 plus sine x, so it's the same thing with the opposite sign. I do that on the top and bottom to keep it even. And on the top, I'm going to just keep it factored for the time being. We'll see if we need to multiply it out in a little bit. But look at what happens on bottom. You get 1 times 1 is 1. And the outside term is going to be minus sine x, and the inside is plus sine x, and they cancel. And that always happens with conjugate. Because of that changed sign, you get a plus minus of the same thing, and they cancel. And then the last term is going to be a minus sine squared x. So here's the cool thing that does in trig land. It will always create a Pythagorean identity if it's 1 and a trig function. So look, if I take this sine squared and move it over to the other side, I get 1 minus sine squared. And this pattern right here, you should start to really, really recognize that. That should send flags off Pythagorean. Anytime you have a squared and a 1, you start looking at your Pythagorean identities. So this changes the 1 minus sine squared x. I can replace the cosine squared x with it. And what that does is oftentimes creates something that will cancel, first of all. Okay, so this cosine now cancels with one of those cosines. But the other thing that it does is it moves the position of your plus or minus sign. So let's take a look up top at the beginning here. See, this was our original right here, and I had the 1 minus sine x on the bottom. Well, now look at it. After I multiply by the conjugate, the one with the plus minus sign and the sign is now on the top. So it kind of changes the shape of your fraction. Instead of addition being on the bottom, addition subtraction on the bottom, now addition subtraction's on the top, which can be really advantageous, especially if you want to split up your fractions. Because up here, I don't want to split up fractions because I've got 2 terms on the bottom. Splitting fractions is best done when you just have 1 term on the bottom. So now look at what we've got. I've got a 1 over cosine x plus sine x over cosine x, which is going to be secant plus tangent, which is my left-hand side, or my right-hand side. Okay? So that's how what the conjugate looks like. Let me show you one more. I'm actually going to do this 2 ways. One is I consider a very hard way, but I want you to see some of those as well. So on this, you're going to see one of 2 things first off, I think. I do notice that this is a Pythagorean identity, so I could substitute that, which is a good idea. I also see that I've got 1 term on the bottom here, and I could split this up into 2 fractions, which is also an option. I do see that I could write this in terms of sine and cosine. Sometimes that is challenging because you're creating a lot of fractions on top of fractions. Okay, so the first way that I'm going to go is I'm going to split up this left side into 2 pieces. So it's going to be 1 over cosine and cosine over cosine. So this is going to be secant x plus 1. Well, that's good, because at least now I've got a secant on the left, and I do have secants on the right, but it's still complicated on the right. Now, what you can do is you are allowed to work on both sides of the equation. You just can't move anything over there. So I could draw, my divider line just so I don't get tempted to move things and say, okay, I've kind of pulled this secant down to its bare bones. Let me go over here and see what happens. My Pythagorean theorem, just to remember for tangent, is tangent squared plus 1 equals secant squared, which means that tangent squared is secant squared minus 1. So this is what I'm going to replace for my numerator on this right-hand side. And one thing that I like about these, first of all, it puts my top and bottom in terms of the same thing. That's good. It also creates a difference of 2 squares on the top. This can be factored. Okay, so those again are patterns that I want you to start picking up when you see two things squared and subtracted. And because that's factored, we can now cancel top and bottom factors. And I'm left with secant x plus 1. Okay, so that's one way to do that problem. The second way I think is a little bit harder, but I want to show you what it looks like anyways. So we're starting with, I lost my problem. Yeah, 1 plus cosine x over cosine x. All right, so some of you might have noticed, hey, this is the pattern that you just told us about for the conjugate. Good job if you saw that. Let's take a look. Let's do it. Let's multiply by 1 minus cosine x on the top and bottom. Now, the thing, too, that is a clue that this is a good idea, is look at my original fraction here, and I have my addition on the top. In this fraction over here, my addition subtraction is on the bottom. That's another clue that multiplying by the conjugate is a good idea, because that's going to switch when I do this. Okay, so my top, I'm going to get 1, and then plus cosine minus cosine cancel, and then a minus cosine squared. And that always creates a Pythagorean theorem. Okay, so remember that sine squared plus cosine squared equals 1. So that means if I want to create this situation, I need to subtract the cosine over. All right, so that means I can replace 1 minus cosine with sine squared x. Okay. Now, at this point, probably normally, and for most students, I would say, you'd look at this and go, I do not know what to do next. Maybe you'd try to multiply out the bottom, but it doesn't seem to be going anywhere. So for a lot of people, this would be an idea, like this would be what it looks like to be in a hole. And you go, this isn't working very well. I'm going to go try something else. And maybe you stumble into this path up here. Okay, but I want to show you another trick. It's very tricky, but it works. So I kind of have the format down. Do you see this? I've got a squared on the top, and then I've got like some sort of like trig function with a 1 and a minus on the bottom. This guy's out of place, but I'm close. So what I'm going to do is I'm going to create what I want over here. I want a tangent, and I've got a sine squared. So the way I create a tangent with a sine is I divide it by cosine, because tangent is sine over cosine. Okay? Now, that is only legal on a fraction if you do the same thing to the bottom. So here's the bottom. And I have to divide that by cosine squared as well. So I take one part of my fraction and I force it to be what I want, and then I compensate for that downstairs. Okay, so now I can rewrite this as tangent squared. And what happens down here? Well, it's all factored. So this cancels with one of these. And I'm left with 1 minus cosine x over cosine x. And this bottom, see, I don't want to flip this up because I don't want to mess up the tangent that I have upstairs that's exactly like I want it. But I might notice that this cosine will split up here. So what that's going to do is give me my tangent squared on the top, and then I've got a 1 over cosine minus 1. Or, sorry, let's not reduce that quickly. Cosine over cosine. Okay, that splits up into the 2. So what that reduces to is secant minus 1, which is what I started with on the right hand side here. Now, I would consider that super tricky and some pretty creative math, but I want you to see that a hole's not really a hole. It just might be hard to get out of it. And if it's getting too hard, like I would say if you are 4 or 5 lines into a problem and still not making headway, that you might want to try a different direction. Depending on how much work you show, maybe 6 or 7 lines. But these aren't intended to be like really, really hard. Okay? All right, so the way the homework works is there's 2 1-5 assignments, and you are set up to do both of them. There will be some triangle problems, and there are actually 2 sets of these solving equations problems because I broke 1-5 is supposed to be a 2-day section, but since we're in a 2-a-day class, that means it's 1 full day for you. So don't hurt yourself doing problems. There's a lot, okay? Because I just assigned a lot because practice is key. If you feel like you're getting it, move on, okay? Do as many as you need to feel competent with these things. And any that you don't know how to do, you can come to office hour, get some help, and then make sure you go back and try them again, okay? These are not easy to make up because they actually have to be equal. So most homework or most test questions will look very similar, if not exactly like the homework. So that's where you want to live for studying. And if you have any questions, let me know. Have a great day.